Hey, what's up everyone? Today we're going to be doing the thermochemistry section of the 2023 USNCO local exam. So that's questions 19 through 24. Let's start with question 19. The amount of energy released by a chemical process is always equal to that absorbed by the system and surroundings. This is a consequence of which law? So we have, four laws of thermodynamics. Let's just go over them really quickly. The zeroth law tells you that if you have three systems, A, B, and C. If A and C are in thermal equilibrium with each other and B and C are in thermal equilibrium with each other, then that means A and B are in thermal equilibrium with each other. Now, does this really apply to our situation? Not really. Let's go to the first law. The first law is your stereotypical energy can't be gained or it can't be created or destroyed. The specific law states that the change in energy of a system is equal to the amount of energy coming into the system minus the work that the system does. And does this apply to our problem statement? Well, it kind of does. The amount of energy released by a chemical process is always equal to that absorbed by the system and surroundings. The amount of energy absorbed by the system is going to be the heat. And the amount of energy absorbed by the surroundings is going to be the work that system does. So energy gained by the system is going to be lost by energy gained by the surroundings is work done by the system. So the first law does apply to our situation here. Let's just go through the second and third law. The second law tells you that in a spontaneous reaction, the entropy of a system always increases. That doesn't really apply to our scenario. And then the third law tells you that the entropy of a pure crystalline solid at 0 degrees Kelvin is equal to 0. That also doesn't really apply to our situation here. This was kind of a brief summary of the laws. If you need to learn about the laws, then I recommend you watch a video on that. Hey everyone, I just want to say if some of these explanations seem a little fast-paced to you, then I have a lot of videos on my channel that are more tutorial-based. They can help you learn the content and then come back to these tests to take full advantage of them. Also, if you're enjoying the video, please feel free to leave a like and subscribe. As far as I know, these are the only videos on YouTube that have work solutions for the USNCO, so a like and a subscription would help it reach more people. And that's it. Thanks guys. Enjoy the rest of the video. All right, let's move on to question 20. What is the standard free energy of formation of NO gas at 298 Kelvin? And you're given a table of the NO gas, the entropy values, the entropy values, and also those values for nitrogen gas and oxygen gas. So since we're dealing with the formation value, let's write out the chemical equation of the formation of NO gas. So that's going to involve nitrogen gas and oxygen gas coming together to form NO gas. And the thing about formation equations is that you need the coefficient in front of your target compound to be 1. And so in order to balance this equation with a 1 in front of the NO, you need to have a 1/2 in front of the nitrogen and a 1/2 in front of the oxygen. Now, why is this helpful? Well, your free energy, your standard free energy of formation is going to equal your standard entropy of formation minus temperature times the entropy, the standard entropy of formation. One of these values you have your enthalpy, standard enthalpy of formation from this table. It's 90.3. So let's plug that in. We have 90.3 kilojoules per mole. And you also have your temperature. You know this is happening at 298 Kelvin. But the thing you don't know is going to be your entropy, your standard entropy of formation. What we do have though are going to be the entropy values of your product of your reactants. And so in order to find the entropy of formation, we can calculate that from our individual entropy values that were given in this table. So our entropy, our standard entropy of formation is going to be the sum of the standard entropies of the products minus the sum of the standard entropies of the reactants. So what are those? Well, the product is going to be nitrogen or NO gas, and that has an entropy of 210.8 joules per mole Kelvin. So 210.8 joules per mole Kelvin, and we want to subtract this from that of the reactants. And if we look at the value for nitrogen, that's 191.6, but you're going to have to multiply that number by 1/2 since you have a 1/2 in front of the nitrogen in the reaction. So 1/2 times 191.6 joules per mole times Kelvin. And then you're going to have to add the other one. So 1/2 times the one for oxygen, which is 205.2 joules per mole times Kelvin. And so what does that come out to? Let's do out the math. 210.8 minus 0.5 times 191.6 plus 0.5 times 205.2. That is 12.4. Okay, so let's plug this value back into our equation here. So 12, since we're dealing with kilojoules per mole, let's convert this to kilojoules. So 12.4 joules is 0.0124 kilojoules per mole times Kelvin. And let's plug that into our calculator. So 90.3 minus 298 times 0.0124, and that is 86.6 kilojoules per mole, which is answer choice B. All right, let's move on to 21. Which statements about entropy, enthalpy, and energy are correct for the reaction below? Okay, so one says your change in entropy, standard entropy, is greater than 0. If you look at your reaction, all your reactants and products are gaseous. Now, what that allows us to do is compare the number of particles that are on the reactant side and the product side. As you can see, there are a total of 9 compounds, molecules on the reactant side, but a total of 11 molecules on the product side. So since you went from 9 to 11, that's gonna mean that you increased your entropy. You have more particles, more randomness. So your change in entropy is greater than 0. And then 2 says your change in enthalpy, your standard enthalpy, is greater than your change in the energy. So if you remember your equation for enthalpy, change in enthalpy is equal to change in E plus pressure times your change in volume. Okay, so in this reaction, we've already discussed that you produce more molecules of product than you have reactants. What that's going to do is that's going to increase the volume. So you know that your volume is going to be, your change in volume is going to be a positive number. And what that means is that your change in energy is less than your change in enthalpy. It just has to be. If this is a positive value, then your change in E has to be less than that of your change in enthalpy. So 2 is also correct, therefore our answer is C. All right, let's move on to question 22. 4 mils of 2 molar aqueous sodium hydroxide is added to 100 mils of 0.2 molar aqueous NaHSO4, all initially at 25 degrees Celsius in a well-insulated flask. Neglecting the effects of dilution and assuming that the volumes are additive and that all solutions have the same density and specific heat capacity as pure water, what is the final temperature of the mixture? Okay, so let's figure out what reaction is actually happening here. You have sodium hydroxide reacting with NaHSO4. Now the thing is, your sodiums are just going to dissociate. So let's just write out the net ionic equation that's happening here. What's really happening is that your hydroxide is reacting with your HSO4 minus, and then what that's going to produce is your sulfate ion and a water molecule. So that's the reaction that's actually happening. Now we are trying to find out the change in temperature. And the way we do that is by figuring out how much heat was produced in this reaction. In order to find out how much heat was produced, we need to figure out our change in enthalpy. So our change in enthalpy is going to be the sum of the enthalpies of formation of our reactant of your products minus the sum of the enthalpies of formation of your reactants. So what are your products? That's going to be your sulfate and your water. And so sulfate is negative 909 kilojoules per mole. And then water is going to be negative 286 kilojoules per mole. And then your reactants minus, that's going to be hydroxide, which is negative 230 kilojoules per mole. And then plus the HSO4 ion, so negative 886 kilojoules per mole. And let's plug this big thing in. So let's do negative 909 minus 286 minus negative 230 minus 886. So your change in enthalpy for this reaction is going to be negative 79 kilojoules per mole. Now that's great, but we got to find out how much heat was actually produced in this reaction. And this tells you your change in enthalpy, but in order to find actual heat, you're going to need to find out how many moles of this reaction occurred. So how many moles are actually getting reacted here? So in order to find that out, you have to go back to your problem statement. You're told that 4 mils of 2 molar aqueous sodium hydroxide was added, and 100 mils of 0.2 molar NaHSO4 was added. You have various amounts of both your reactants, so one of them has to be the limiting reactant. Let's figure out how many moles of sodium of hydroxide we have, and how many moles of HSO4 minus we have. You're told that you have 4 mils of 2 molar, so let's do 2 molar times 0.004, so that is 0.008 moles of hydroxide. And then HSO4 is going to be 0.2 molar times 0.1 liter, which is 0.02 moles. And since these are in a 1-to-1 ratio, it's pretty clear that hydroxide is your limiting reactant. Then that means only 0.008 moles are actually being reacted. So we can use that to find out how much heat there was. So let's do negative 79 kilojoules per mole times 0.008 moles. Let's do negative 79 times 0.008, and that is negative 0.632 kilojoules. All right, so that is how much heat was released into the system. We have to now turn that into a change in temperature. So in order to do that, let's use Q equals mc delta T. We know our Q, we're trying to find our delta T, so let's isolate that. That's going to be Q over mc. Q, as we found out, is going to be 632 joules. And I'm turning this positive because our negative 0.632 is from the perspective of the system. It's going to be from the perspective of the reactants. But as we're told, we're looking for the change in temperature of the mixture. So we're looking at how much energy was put into the surroundings, which would be a positive value. It's going to be the positive value of this. So that is 632 joules. Divided by mass times heat capacity. Well, mass you can get from adding up the volumes. It is 4 mils plus 100 mils, which is 104 mils. And the problem tells you to assume that the solution has the same density as that of pure water. And pure water is 1 gram per mil. So 104 mils is going to be 104 grams. So 104 grams times the specific heat capacity of water, since we're told to use that of water, is going to be 4.18 joules per gram. And so let's plug this all in. We have, let's make a fraction, 632 divided by 104 times 4.18. That is 1.45 degrees Celsius. So if you have a change in 1.45 degrees Celsius and it was initially 25 degrees Celsius, and you know the temperature went up. Let's add 25 plus 1.45. That is going to be 26.45, or answer choice C. That was a long question. Let's go to question 23. The KSP of aluminum hydroxide is that at 298 Kelvin. What is the standard change in free energy for the precipitation of aluminum hydroxide according to the equation below? So you have to understand what you are given. The KSP refers to the K value of this reaction. It's the one of aluminum hydroxide dissociating into its ions, 3OH minus. But what we're looking for is the change in free energy of the precipitation of aluminum hydroxide. So what we really want is the aluminum ion and the 3 hydroxide ions coming together to form this. And so we're actually looking for the inverse of this. Now, why is that information helpful? Well, you have a equation for your change in free energy with respect to K. Your change in free energy, your standard change in standard free energy is going to be minus RT natural log of K. Now, the K that you're given is again the KSP, but you want the opposite of that. And since you want the reaction that is the inverse of that, all you have to do is take the inverse of the KSP. Now, what that effectively does is that if you go back to your algebra notes, if you take the inverse, let's say you have natural log of K. Natural log of K is going to equal the negative natural log of the inverse of K. So we can take our little equation here and say that the change in free energy is equal to RT, the natural log of KSP. And that's just using the fact that you're given KSP of this reaction, but you want the inverse of that reaction. And so the inverse reaction is going to have a K value that is the inverse of the KSP, and therefore you can just get rid of the negative sign. And from here, it's just basic math. The R value that you want to use is 8.314. I'm just going to not write units, 8.314 times temperature, which is 298 Kelvin, times the natural log of your KSP, which is 2 times 10 to the negative 31. And so let's plug that in. 8.314 times 298 times the natural log of 2 times 10 to the negative 31 is that. So negative 175 kilojoules per mole. And that is answer choice A. All right, let's move on to 24, which is the last question. The vapor pressure of solid I2 is measured in bar over the temperature range 0 to 55 degrees Celsius. The natural logarithms of these vapor pressures are plotted as a function of the reciprocal of the absolute temperature as shown below. What is the standard enthalpy of sublimation of I2 solid? Now this equation has an equation that is kind of necessary to solve it, and it tells you that the natural log of K is equal to your minus enthalpy of standard enthalpy of sublimation over R times 1 over T plus some sort of constant. And this might look familiar because that is the exact format that this equation is in. As you can see, your Y is your natural log of vapor pressure, which is what you have here. And then your X is 1 over temperature, which is what you have here. And then your C is some sort of constant. So essentially, if you look at the equation that you're given for this line, that value is your constant, and this value here is your magic number over here. So negative your enthalpy, change in enthalpy of sublimation over R is equal to negative 7527. This is really helpful because this value is exactly what we want to calculate. So if we just do, if you multiply both sides by negative R, that's going to be 7527 times R. And so the R value that we want to use is going to be 8.314. Let's just do 7527 times 8.314. And that is 7 527 times 8.314. That is 62.6 kilojoules per mole. And that is answer choice D. And that was the entire section. Whoops, that went a little off screen. But yeah, that was the whole section. I hope you were able to learn something. I hope this was helpful. Thank you for watching, and I'll see you later. Thank you.